Okay, so today's set of notes, what we're going to do is first take a look at an example very similar to the example that we did previously. Let's kind of scroll back up and take a look at the previous example. That what we did in example 5 was we were looking to find the point on the curve closest to 3, 0. So when you see that we're looking for a closest, we realize that we're trying to minimize distance. We used the distance formula to come up with a primary equation, but we realized that kind of a shortcut that we're going to pretty much do in all optimization problems is that I can find the location of the minimum on the distance function by minimizing also the square of the distance function. And basically that just makes an easier derivative for you. We used our constraint, which is the point happens to fall on the curve that we're looking for. So we have the curve's equation. Substitute that in, and then we found our relative domain was a closed interval, and then we used EVT in order to determine what the solutions or what was the point that was closest to 3, 0. So when we get through example 5, you've seen some examples where we used a modified first derivative test. You've seen examples of where we've used the modified second derivative test, and you've seen an example where we've used the extreme value theorem. Now, what I want to do in example 6, which is a very similar question, is take a look at example 6, but we're going to do that one with a calculator. So we're just going to kind of show you all the different aspects that you might see on the AP, and we're going to assume that this would be on the calculator section and kind of talk about how we're going to do that. So again, we're trying to find the point, so we're trying to find the coordinates x, y. They're going to be on the curve y equals cosine of x, and we're trying to find the point closest to the point 0, 0. So closest means that we're going to minimize our distance. And again, I'm pretty much immediately going to turn that into the distance squared. So I'm going to minimize the square of the distance. I'm just going to call it d, which is going to be your change in x, x minus 0 squared, plus your change in y, y minus 0 squared, which gives me x squared plus y squared. Now, just like we did before, we're going to use a secondary equation to help a constraint that's going to help me substitute. The beginning part, whether you have a calculator or you don't have a calculator, the setup is the same in all of them. The difference will come in how you complete the calculus. The constraint, the point that we're interested in, is on the curve y equals cosine of x. So I'm going to use that to come up with a relationship between x and y. So I use that to substitute, and my primary equation is now going to become that this squared distance is going to be x squared plus cosine squared x. Right? At this point, I am going to then think about what the relevant domain is going to be. I'm going to use my calculator, however, to graph this. So I'm actually just going to pause for a second, and I'm just going to graph the equation and then use that to help me, even though you pretty much know what we're going to be looking at. Actually, we won't graph it. We'll do it on the initial part over here. If I graph the curve cosine of x, which, like I said, this is why I didn't need a calculator for that, we know what the cosine looks like. Maybe not as a little even down here, but we're looking for the point closest, the point on the curve closest to the point 0, 0. Now, I understand that you can probably guess which point is going to be the closest, but maybe we're not sure. But we could definitely agree that it's going to be kind of a point that lies on this section of the curve. That once I get beyond this intersection point, it's going to be a longer distance. So it would have to be somewhere kind of along these choices going around. So the intersection point of cosine, when it's cosine of x equal to 0, that's going to happen at pi over 2 and at negative pi over 2, using our knowledge from trig. So that's going to give me a relevant domain for this problem of negative pi over 2 to pi over 2. And since I see that this is a continuous function, this square distance is the sum of two continuous functions on a closed interval, so my method is going to be EVT. All right, so the setup is exactly the same as before. Now we're ready to basically do the calculus. After we have our primary equation ready to go, we're going to need to take the derivative, find our critical values, set up our chart, and then look for the closest minimum value in our chart. So we're just doing basically EVT. So before I show you the chart, I brought it in from the calculator down here. We could do this by hand, but you're going to get 2x plus cosine of x, and then you're going to have to set that equal to 0. So that's why this is a calculator problem. So what we're going to do is we're going to show you how we would do this on the calculator. So what I'm going to do is I'm going to input my function into the function that I'm trying to minimize, x squared plus cosine squared x, into my y equals, and make sure that your calculator is in radian mode. All right, so we get our square in here. I'm just going to do zoom trig. I mean, you really just need negative pi over 2 to pi over 2. And that would be fine. This will just verify what we would expect to see for the square distance. Okay, and what we see on this, now if I didn't have to use calculus, I clearly see that it looks like the minimum is happening when x is equal to 0. But now let's use our derivative to come up with this. All right, so I'm going to turn off the original function. I'm going to come down and I'm going to use my Math 8 in order to input my derivative. And so we're going to go get y1, vars, y-vars function, y1. And we're doing that with x equal to x because I want to look at the graph. All right, and I take a look and you wait a little bit while it thinks about it. But remember that we find the critical values are going to occur where the derivative is equal to 0. This was a continuous and differentiable function, sum of continuous and differentiable functions. So, and again, we're not going to guess. We're going to go ahead and say, why don't we actually find this? So I'm going to do my second calc. All right, we're going to choose our 0 because we want to find the x-intercept. Pick a number a little bit to the left, -1, a little bit to the right. I'll just do 1. And my guess, I'm going to guess 0, but it doesn't really matter. We'll let it come up with it. And because I guessed 0, it got 0. Now I do want to show you something. I did this earlier, and so I just want to kind of see if I can recreate what happened earlier. So if I do negative, maybe just picking different bounds, and negative, or sorry, I need a positive for that one, delete, and 2. And then suppose I just do my guess as maybe not necessarily as close as I did because I was thinking it was 0. And it's thinking. Yeah, okay, so now see, take a look at what you got down here. When I guessed 0, it told me 0, 0. Now remember, it's doing a guess and check in order for it. And because I didn't really start at the exact value, its guess and check gave me this as an x. Are you going to write that down? No. You are going to be smart enough to recognize that a -2 times 10 to the -4 is essentially 0. That if I hit trace and plug in 0, I see that 0, 0 is actually the point. That's a kind of a rounding error that I'm not going to worry so much with. So we're going to go with 0, 0. Okay, so x equal to 0 is going to be my critical value. So to write that up in terms of my work, I would say d prime is equal to 0 when x is equal to 0. And because I'm doing EVT, I know that in terms of my chart, which you see I have it started over here, this is from the calculator, but what I'm going to do is what I'm going to write down. Now make sure you pay attention. Don't just do x, y. It's x and the square distance because that's what we're trying to minimize. We're going to put in our negative pi over 2, 0, and pi over 2. So those are going to be the values of interest. And I am going to use my calculator to go get those values. I am going to do the same thing that we did before that I showed you in class. Make sure your table setup is on Ask. And then when I go to the table, what you're going to do is you're going to type in your pi divided by 6 you're going to type in your 0, and then you're going to type in your, oh sorry, it's not supposed to be pi divided by 6, it's supposed to be pi divided by 2. And then 0, and then our negative pi over 2. Right? And then we can take a look at our values that are over here. Now, you want to be careful. These are not the values of interest. I need to go back to my y equals. Remember, I'm not trying to find the derivative. Turn that off. Turn back on your original function. It's that squared distance that I want to see in the table. And so these are the values that I'm looking at. And I'm looking for where the squared distance is at a minimum. And the squared distance is at a minimum right here for x equal to 0. So let's talk about our explanation. And like I said, and I brought this in because I didn't really feel like copying it over, but you would simply be on your table for your work, because you can't obviously copy and paste, is put in your 3 decimals. All right, now just to finish up the problem and what we want to be careful, remember, what did they ask us to? We know that based on the calculus we've done, by the extreme value theorem, okay, D was continuous on our closed interval negative pi over 2 to pi over 2. So x equal to 0 minimizes D. That's pretty much all you need. I've met my conditions. It was continuous. It was on a closed interval. And based on the fact of the information I have over here, the smallest value is 1. So x equal to 0 minimizes D. It is a global or absolute min, which is what we're looking for. So maybe I might want to add that it's an absolute versus a relative to make sure we know that. X equal to 0 is the location of the absolute min on D. Now, what did they actually ask me for? Find the point on the curve. Now, be careful, don't choose 0, 1 because there's a 1 in the chart right here. When x is equal to 0, you need to actually find the y value. You go y equals cosine of 0, and yes, it does, by happenstance, happen to be the point 0, 1. But I wanted to be careful here to say, look, don't just pick what's in the table. That was your squared distance. That what you had to do was to go find the point on the curve, which is going to be cosine of 0, which does happen to be 1. Also, make sure you look and see whether they're asking you for the point or what the distance is in different things. And make sure that if you're using that shortcut of the squared distance, but they ask you to find the distance, remember that the square distance is equal to the actual distance squared, so you would use that to solve for your distance if that's what they ask you for. So just wanted to mention that. All right, so at this point you've seen all of our calculus techniques in play. You've seen the modified first derivative, modified second derivative, EVT without a calculator, EVT with a calculator. So what we're going to do for the remaining examples in this packet is I am going to basically do the setup. Your job is going to be to finish the problems out and actually find the maxes or the mins. Because what I want to concentrate on is how to set the problem up. Once you set the problem up, it should be fairly straightforward to apply your 3 options, your 3 methods for finding the global extrema. All right, so let's take a look at example 7 and start working through reading it and our setup. We want to find the largest rectangle that can be inscribed under the curve 16 minus, and this should be 16 minus x squared, in the first quadrant. Now let's talk about this whole idea of make sure you read carefully the entire problem. This is not a related rate problem. They're not asking me for how fast. They're asking me to find a largest, so I know that this is optimization. What does it mean to find the largest rectangle? What do you think that we're actually going to be maximizing? And hopefully you'll be like, hey, we're going to maximize the area. So we're going to maximize our area. And we know that area of a rectangle is going to be my length times my width. Now, in a lot of these problems, it may be helpful to draw a picture. so that we can kind of see what we're looking at and help identify our variables. Now, when I draw this in, 16 minus x squared has x-intercepts at -4 and 4, and a y-intercept of 16. So we just have a nice upside down parabola. I guess technically I'll keep it going there. And we are going to be inscribing a rectangle in the first quadrant. This is something important. It's not always in the first quadrant. It might be a rectangle just under the curve. But this is a rectangle in the first quadrant, and inscribe means like your corner is going to be just touching it. And so this is a representative rectangle of what we're looking at. And so we need to decide what's kind of important here. What is important, this point right here that's on the curve, I'm going to call that point x, y. And then I'm going to look at that and say, well, how is this point, x, y, related to my length and my width? My width is going to be x, and my height is going to be y. So my formula, primary equation, basically becomes area equals x times y. Now in problems like this, you're going to be looking for a constraint. What is the constraint that is going to have a relationship between your two input variables, x and y? Where is this point that is touching the curve? It's on the parabola, 16 minus x squared. So my constraint is going to be the curve. It's very similar to what we did in the previous problem. So I'm going to use this to substitute. So my primary equation that I'm actually going to be taking the derivative of and using the three methods for finding global max is going to be area equals x 16 minus x squared. This is going to simplify. It's going to be easier to take your derivative if you go ahead and multiply it through. So that's going to get me to here. So the actual equation that I want to maximize using one of our three methods is going to be this. We look for a relevant domain so that I can then decide which of the three methods is going to be appropriate. Now x, think about your rectangle. Since I have to be in the first quadrant, you should probably agree that your relevant domain has to be bigger than 0, because if x is 0, you don't really have a rectangle. And also, the largest that x can be is going to be 4, because we're being inscribed under the curve. So we need to make sure that we stay over within the bounds between when you hit the end of the quadrant 1. So I would go 0 to 4. Now this is an open interval. So in terms of method, what you need to do is either do a modified first derivative or a modified second derivative. Now what I would like you to do in terms of your calculus is I would like you to find your max area by doing the modified second derivative test. And so that is kind of your strategy to go back. But now that you see the setup, that should be fairly straightforward. And then we will check that in class next time. All right, now let's look at example 8. And let's talk about the setup for example 8. Now in this one, we've got an open-topped box. I'm going to highlight that because there's no top to my box. It's got your sides and your bottom, but no top. And it's going to be constructed from a square piece of cardboard. It's going to be 3 feet wide, and we're going to cut out a square from each corner and bending up the sides. So this is almost like those intelligence tests that you take. I have a square piece of cardboard. I'm going to cut out a square from each corner, and obviously I'm going to cut the same square out from each corner. And then when I do that, okay, see if you can visualize, I am going to then fold it to make the sides. So I want to fold here, I'm going to fold here, here, and here. And after I make that fold, the box that I get will look like this, where let's match up our sides. This edge right here comes from this fold, where I folded this up. So let's call this cut that I make x. So that would be x. Now this side right here, okay, our length, the entire side is 3. But that's not this entire side right here. Remember, because we cut 2 little pieces off of my length. So this inside little piece right here is going to be 3 minus 2x. And then because it was a square piece of paper before I cut the same amount, that is also going to be 3 minus 2x. Now when you're doing this problem, what sometimes can confuse people is you're basically trying to find the largest volume. So again, we know that this is an optimization problem. I am trying to maximize volume. And volume is length times width times height. So I actually have 3 variables in this problem that I need to find a relationship between. But if you draw the picture like I have done here, you'll see that the variable that I want in the problem is not length, width, or height. Height is actually going to be the one that we want. We want our height because that's what I'm calling the x over here. And so this W and L, I can see from my picture, I can get those in terms of x. So it's almost like you have a system for your constraints. And a lot of times, sometimes you don't even really write your constraints down separately. You just realize that my length is 3 minus 2x and my width is 3 minus 2x and my height is x. That I use the picture to help me come up with where these constraints are coming from so that I can make my formula equal to 3 minus 2x squared times x. Now you could FOIL this out and make it all into a power rule to take the derivative, but it's easy enough with chain rule and product rule to go ahead and just do that here. All right, now let's talk about our relevant domain. My relevant domain in this problem, x is the cut that I'm making. And hopefully you would agree that I have to cut something out, right? And then as I make cuts, depending on how big the cuts are, at some point there's going to be a problem that I can't make a cut bigger than half the distance, because once I hit 1.5, I don't have anything left to actually fold. So it's going to be a domain of 0 to 1.5. And again, it's an open interval on this one. And so we're going to have to use either the modified first or the modified second. And again, so I've set it up and it's ready for you to go. You're looking for the maximum. Here's your primary equation. Here's your relevant domain. In this problem, since I used modified second and the one above, I would like you to use your modified first derivative test for global extrema. Okay, and so I'll leave that for you to do. Let's take a look at the next example. All right, we'd like to start not always looking at rectangular three-dimensional objects. We start looking at things like cylinders and cones and spheres. So we're going to start this problem with a cylindrical aluminum soda can. So it's a right angle to the bottom. We have a circular base, 2 circular bases. It's going to hold 12 ounces of a tasty beverage. And we want to know what are the dimensions of the can that will minimize the amount of aluminum used. So it's definitely an optimization problem. So we're looking for minimizing the amount of aluminum used. What are we talking about when we say amount of aluminum? That would be the aluminum you use for the top and the bottom and for the sides, which is nothing more than surface area. So we're trying to minimize surface area. Now let's talk about surface area of a can like this. Obviously the area of the bottom and the top are 2 circles, right? So we have cut out from our aluminum sheet, and we'll assume that we're just going to cut out a circle, and then if we need to bend it, we'll do that. But we're going to cut out 2 circles of equal size. And what is the area of those 2 circles? The area of a circle is pi r squared, and we have 2 of them. Now we're going to imagine, again, we have to have some spatial reasoning. Pretend that you cut your can right down this. You've taken the top and the bottom off, so you basically have this open top, open bottom cylinder. But we're going to cut that cylinder so that if I'm looking at it, kind of expanding it out with the cut and taking it apart, I'm going to unwrap this now. And I'm going to lay it out flat so I can say, well, what kind of shape would that be? That shape is going to be a rectangle. Now, this part of it is nothing more than the height of my can, so that's going to be h. But the length here comes from this unwrapping of this section right here. And that's nothing more than going to be the circumference of the circle. Circumference of a circle is 2 pi r. So the area of the sides, surface area of the sides, is going to be the area of this rectangle. So it would be 2 pi r times h. So that's my first setup for my primary equation. I have surface area, which we can just call S, equals 2 pi r squared plus 2 pi r h. Now my problem is I have two inputs r and h. So I need to find more information in this problem to get a constraint that relates r and h together. So we look up and say, well, what else did they give us? Well, 12 ounces, that's the amount of liquid in the can. So we'll assume that this is really talking about a volume. But notice they gave me some more information, gave me a hint, and said 12 U.S. fluid ounces is this many cubic inches. So we must be measuring radius and height in inches, and I needed cubic inches so that I could get my volume is going to be this 21.6562. But remember, I'm trying to get a relationship between length or radius and height. So I think, well, what do I know about volume? Volume of a cylinder like this is the area of the base. Volume equals area of the base, pi r squared times the height. That's one of those formulas that you should know. And so I do sort of have a system. I know the volume and I know a formula for the volume. So I can put them together to get that pi r squared h is 21.6562. So now I can use this as a substitution. Now you have a choice. You can solve for r squared, but then you have an r over here. I don't really want to solve for r substituted in two places. I would solve for h and make the substitution. So h is going to be 21.6562 divided by pi r squared. So that's what I'm going to use for my substitution. So my primary equation is going to become S equal to 2 pi r squared plus, and when I do my 2 pi r times my h, 21.6562 over pi r squared, I am going to simplify it. That I can cancel the pi's and I can cancel one of the r's out. And then I have 2 times 21.562 over r. Now if you had a calculator you could multiply it out, but it's okay. We're going to be able to do it without multiplying out the number. You can double it if you want to. But basically what we're going to be looking at here, and I also, because it's over r, I would like to go ahead and bring the r up. So 2 times 21.6562 is going to be 43.3124, and this is r to the negative 1. So now that's what I'm going to use to take the derivative. I need to find a relevant domain. Now when I'm looking at this, my variable is r, so I'm trying to find information about r. Now I'm going to use this information right here. r, you definitely have to have a radius, so we're going to start from 0. As r increases, okay, because it's in the bottom in this formula in my constraint, as r increases, h is actually approaching 0. And it's kind of asymptotic, but it's not ever going to get to 0, because if r was like 10 million, I could make h small enough. That just makes h a really small number. So technically our relevant domain is going to go 0 to infinity. All right, and so then that's our setup. We can't use EVT. We've done a modified second. We just did a modified first. I don't necessarily, I don't know, let's go back and do a modified second derivative on this just for practice. So when you guys go to solve this one, do a modified second derivative test to do as your justification for this one. We'll kind of alternate around on those. All right, so now let's look at example 10. So we're going to leave a little bit of the geometry behind, which is what we've been kind of doing up until this point. And we're going to look at, sometimes we don't really have a picture, sometimes we need to look for a pattern. So let's read through example 10. All right, in example 10, we have an 80-unit apartment complex, and we're trying to decide what rent we want to charge. So I'm going to circle the 80, that's important. And we've shown that if we had a rent of 200, all of the units will be full. On average, if I increase the rent by $20, I will have a vacant unit. Each time I increase by $20, somebody says, no, I'm not paying that, and so I have a vacant unit. Okay? And I want to find the rent to charge so as to maximize revenue. So in this one, you're like, well, we definitely know that our primary equation is we're going to maximize revenue, and to figure out revenue, you're basically going to take your rent times the number of apartments that you rent. And at that point, you might start to get a little stuck because you're like, I don't see any constraints in here for me to kind of work this out. Well, this is an example of where we're going to let's make a chart. Let's look at our rent. Let's look at our number of apartments that we're going to be able to rent. And then let's look at our revenue. Number of apartments rented. All right, and we'll start with the first example that if I could charge $200, I can rent them all, and my revenue is going to be 200 times 80. Okay, I could multiply it out, but I'm not going to worry about it for this point. If I increase by $20 in rent, that would put me at 220. I can only rent 79 apartments. 220 times 79, whatever that is. If I increase by another $20, I can now only rent 78 apartments. So I have 240 times 78. So now I'm looking at this going, all right, I think that what I need is to introduce a new variable. That what I'm doing is giving rent increases. So let's say that N is going to be the number of rent increases. So this would be 1, this would be 2. And so what I want to do is come up with a general formula for if I have N rent increases, then what would my rent be? Well, how am I finding it? I started at 200, and for every rent increase I went up by 20. So I would have 200 plus $20 for each rent increase. I would look at my number of apartments that I have rented and say that I started with 80, and for every rent increase I lose 1. So 80 minus N. And then we take a look at, well, how am I finding my revenue? My revenue is my rent times the number of apartments rented. So my revenue is going to become 200 plus 20N times 80 minus N. And so what I have done by taking a look at this table is I have created a new variable. Okay, again, it's kind of like a system. I know that I had rent and number of apartments as my two variables, and I can't really get a direct relationship between these two, but there is a direct relationship between the rent and the number of rent increases and the number of apartments rented and the number of rent increases. So I add that third variable in, and that allows me basically to, again, you're getting a constraint system that your rent is 200 plus 20N. Your number of apartments rented is 80 minus N, and then I can substitute those in to get my revenue equation that I'm going to maximize as 200 plus 20N, 80 minus N. Now let's talk about our relevant domain. Obviously, what's the best case scenario? Your best case scenario is to rent all 80. So you would have no rent increases. Well, we'll see if that's the best scenario for revenue, but I could rent them all 80, right? That's possible. And take a look at that revenue. I could also rent none of them. If I increase the rent enough, nobody will want to live there. And so I have 0. So this is an example of where we have a continuous function on a closed interval. So for this one, you're going to go back and you're going to use your EVT method on that, right? But again, this was an example of where we had to basically create a third variable, and we came up with it by looking for a pattern. All right, let's take a look at, oops, let me clear this out because you obviously don't want to see the answers before we start. What I want to do is I want to take a look at this next example 12. All right, so example 12, we're now going to inscribe shapes not under curves, but let's go into the 3D world and we're going to inscribe shapes like cones and cylinders and spheres and cubes into other shapes that are around circumscribe the inscribed shape. So the first thing is, let's talk about the volume of the largest cone that can be inscribed inside a sphere with a radius of 5. Now, maybe before we start this, let's go to the internet and let's see if we can find kind of an animation of what's going on here. All right, so here's kind of this idea, and right now I'm kind of looking straight ahead on this. But what we're basically doing, do you see how the sphere is circumscribed around the cone and that the edges of the cone are right on the sphere? And we can kind of basically, as we move the radii, let's see if I can go this way. Oh, it only wants me to tilt one way. That either I have a really tall, skinny cone, or as the cone gets wider, because it's supposed to always be on the edge, that we basically end up, now this one's going to stop right when it gets to halfway, but it could of course go up higher and become short and small little cone over on this side. So there's no limit. I don't have to stop at the diameter of the sphere, but we're basically going to get this inscribed in it. Now I might come back to this in just a second to kind of talk about some situation, but let's draw our own picture and let's use that to start in kind of figuring out what we want to do here. Oh, and before we walk away from this nice little animation that we have, I'm going to show projection, because what this is suppose I'm just looking at it straight ahead, kind of more of a cross section, because that's going to be important a little bit later. So as I am moving my cone, you can kind of see where the little edges of the cone are by looking at this cross section over here. And so I'm also going to import this in because we're going to use this also as well, kind of as a picture that we want to look at. Alright, so now that we kind of see what's going on, now let's see what we're doing. We're trying to find the volume of the largest cone that can be inscribed inside the sphere, and the radius is going to be 5. So when we're looking at this, I'm going to draw my own picture, so you might need to have some artistic skills here. I'm going to have a sphere, so we draw ourselves a three-dimensional sphere. The radius is going to be 5. That's not a variable, that's a constant in this problem. Then what we're going to do, just to kind of match it up with what I have over here, I draw a cone first by drawing a nice cone all the way to the edges, and then we dot in our part here. The radius of the cone is going to be r. The height of the cone is going to be h. So that's where my variables are coming into play. Okay, so like over here we're going to have a certain radius, and then this part right here, from here down to here, is going to be the height of my cone. Alright, now what we want to do then is we're trying to maximize, find the largest volume of the largest cone. So I want to maximize my volume, and again you'll be given this in the AP, the volume of a cone, which is our 1/3 pi r squared h. Alright, so again we have a primary equation. Now what we need to do is we need to come up with constraints. And our constraints need to be something to relate r and h together. And kind of in this problem, what we need to remember is that as we're doing it, and I'm going to edit this picture, this should be 5 for our sphere, -5, 5, and -5. Now, when we're looking at this, what I'm going to do, you're like, how in the world am I going to get a relationship between r and h other than the fact that they are in this triangle? Well, what we're going to do is we're going to add, from the center of the sphere, draw a radius to one of the vertices, or vertices. This radius of the sphere is constant, it's 5. Okay. Now, the trick to this one is kind of similar to the one that we did in the previous problem, in that we need a new variable to relate r and h to, that we can then use as a substitution. It's almost like a system. The trick to this is to recognize that we have a right triangle. That the triangle that we're looking at, if I can just kind of shade it in right here, that triangle has a leg of r, a hypotenuse of 5, and then this side, let's just call it y for a moment. And so I can get a relationship between y, r, and 5 by using Pythagorean theorem. So y squared plus r squared is equal to 25. And then I look at h and I think, well, is there any way to get h related to y? Now remember that the distance from here to here we also know, because that's going to be my constant of 5. So hopefully as soon as I just put that on the picture, do you see that you do have a relationship between h and y? H is equal to y plus 5. Now this is going to work even when the little cone is up above. Let's draw that kind of, we'll just do a small mini version up here. What if the cone, when I look at the cross section, is this? So your axes are still here and here. Okay? When I draw this to the corner, okay, now in the triangle that we're looking at of interest is now below. I'm still going to call this y, this is still 5, and that's still r. That relationship still holds. And here, when you're looking at this entire part right here is the 5. And the height is now the little small piece that's in here. Does my relationship hold still? Yes, it does. The only difference is my y here is going to be a negative number. So y would be, and I know that looks weird because it's above, but this y, it's going to be positive distance when it's below. We'll make it a negative distance when it's up. All right. Now that's going to help me. Now I'm going to have to figure out my relevant domain, and I need to substitute. Once I get this, you basically have r squared. You can solve this one and get that your r squared is 25 minus y squared. We've got our h is y plus 5, so it's almost like transitivity. You're going to basically put it together so that your volume now becomes a function of the new input, which is going to be y. So 1/3 pi 25 minus y squared times your height, which is y plus 5. So we've changed it so that we have a single input. It happens to be a variable that we had to create, which we only knew to create by drawing the picture and looking for relationships that we could come up with. There wasn't a direct relationship between h and r, but I realized by drawing some right triangles that I can get a relationship to a different section of the graph, and that would allow me to come up with a new primary equation. All right, and so now the y is my input, so I need a relevant domain for the y. Now remember, we said that when it was below, it's positive. So if it's below, it could be, if it's on, it's 0. And then it could get all the way down to, we'll say, 5. But it can't actually be 5 because then that would not have an actual cone. It would just be a line left. And then if I go above, this y is negative, and it would be allowed to get a negative distance all the way up to the tip here, which is going to be -5, and that's going to be open as well. All right. Now, for your method on this problem, since we have an open interval, we cannot use EVT. What I would like you to do is, let's do another modified first derivative here. Modified first derivative. So I'll leave you to do the calculus to solve that using the modified first derivative. All right, so now let's take a look at example 13. Again, working on the setup. We have an arched top window, bottom is a rectangle, top is a semicircle, half a circle. And we want to know if there's 12 meters of framing materials, what is the width of the window that lets in the most light? So most light means we're trying to optimize, maximize the area of this window right here. Okay, so we're going to let in the most light, so we're going to maximize our area. The area of the window, remember you have half a circle, area of half a circle is pi r squared divided by 2. And then you have the area of the rectangle, which is going to be plus my, now let's relate it to the r, right? What's the actual width right here? The width is going to be 2r. And then you're going to have this height. So 2r times h, width times height. So we have two variables. Let's label them in the problem. So r and h, and then we'll make this 2r so that we have that down. So now we're going to be looking for some constraints, and our constraints are going to need to be a relationship between r and h, if we can get that. So we read on, we say, what else did they tell us? There are 12 meters of framing materials. 12 meters of framing materials. This is basically giving you some information about perimeter. That I know the perimeter, basically the max it could be is 12. That I have 12 meters of material to use. So now I need to figure out, well, what would be the actual material that I am going to use? Like if I'm building this in, I'm going to assume that I'm going to need to have definitely a border around the rectangle. So the perimeter for that would be 2r plus 2h. And then I'm going to need the semicircle, which is half of the radius, or half of the circumference of the circle. So that would be 2 pi r divided by 2, or pi r. And that's 12. And you don't need to double do that when you've already done it once. So that's what we're going to assume is our relationship between r and h. Now, what do I want to solve for? More than likely, we could combine these together, but I would solve for h because that's the singleton up here. So I would say h equals 12 minus pi r minus 2r all over 2. So that's going to be what I use to substitute. So my primary equation is going to be a equals r pi r squared over 2 plus the 2r, the 2's are going to cancel. Can I just go ahead and cancel those and simplify and get r times 12 minus pi r minus 2r. And basically, just to simplify to something ready to take a derivative, let's make it pi over 2 r squared plus 12r minus, and I'm going to combine these together, pi plus 2r squared. Now the reason why I did that, this is a constant, so it's going to be a power rule. Alright, now let's talk about our relevant domain so I can figure out what method I'm going to use on this. R is my radius. Obviously, the radius has to be bigger than 0. And as the radius increases, then my h, what's happening to my h? Well, as the radius increases, at some point we can't have h equal to 0, right? So that would be kind of bad. You don't want h to equal 0. So maybe I should solve an equation and say, well, for what value of the radius do I end up with 0 for the height? Because that's not going to be allowed. And so if I multiply this out, I basically get 12 equal to pi r plus 2r, or r equals 12 over pi plus 2. And so that is going to be my max. Now that's not going to be a closed interval, so I definitely need to use either modified first or modified second. And I would like you to do a modified second derivative for this example. All right, and now we're ready to go to the last example and to get that one set up. Example 14. We want to find the equation for the tangent line to the graph of this having a maximum slope. So we want to maximize your slope. And your slope is found by doing your derivative f prime of x. So that's what we're trying to maximize. So my formula that I'm trying to maximize, I'll just say S, because I think you're going to watch why in a second. The slope, which is found by doing the derivative, is going to be, if I come up here to do my derivative, minus 2 minus 2x minus x squared. So I want to maximize this. Now, in terms of my relevant domain, really, this is a continuous polynomial at any x is allowed, so my relevant domain is really minus infinity to infinity. Now, I'm really definitely going to be looking for, going to have to be modified first or modified second. I think let's go ahead and do a modified second on this. And I'll leave you to do the actual work. Now, what you want to be careful of is that when I say modified second derivative, okay, you're going to get confused because the formula was a derivative. Let that go. What you're doing to maximize s is you're going to find s prime and set it equal to 0 to get your critical values. Then you're going to find the second derivative of s, okay, which does happen to be the third derivative of f, and you're going to determine whether that is always positive or negative so that you can use a modified second derivative. And what confuses people in this problem, which I see a lot, is that s prime is actually the second derivative of f, and the second derivative of s is the third derivative of f. And so a lot of people get confused and they try to maximize f instead of maximizing the slope of f. And so that's something to be very careful of there. So I'm going to let you finish out number 14 with the calculus portion of it. Now when we come to class next time, what we're going to do is that we're going to have you work on setup. See, I did the video today and I've done all the setups and you're practicing the calculus portion, which is more work from 4.1 to 4.6. What you will do in class on Friday is I'm going to give you a handout that has optimization problems on it, and I want you to do the setup only. So you're going to do what I did in this video for Friday's classwork.